Thinking Aloud. Conversations on the leading edge of knowledge and discovery with parapsychologist Jeffrey Mishlove.
Hello, I'm Jeffrey Mishlove. Today we'll be exploring black holes, cosmology, and the limits of science. My guest is Professor Bernard Carr, who is a professor of mathematics and astronomy at Queen Mary College, University of London. He received his doctorate at Trinity College in Cambridge, England, under the supervision of Stephen Hawking. He is co-author of the book Quantum Black Holes, and he is editor of the anthology Universe or Multiverse. He is also author of a fascinating chapter titled Black Holes, Cosmology, and the Passage of Time, 3 Problems at the Limits of Science, published in the anthology The Philosophy of Cosmology, and that will be the focus of our interview today, this particular chapter. Once again, this is an interview on the internet. Dr. Carr is in London, and now I will switch over to the internet video. Welcome, Bernard. It's a pleasure once again to be with you.
A pleasure to be here again, Jeff.
And we're going to look at cosmology, essentially, which is perhaps one, if not the oldest of the sciences. It goes back well into ancient times, and it occurred to me that the earliest cosmologists were the Magi and the priests and people who were initiated into an esoteric order that had deep roots in Zoroastrian culture.
Well, of course, it's true that, cosmology is asking very basic questions about the origin of the world and the future of the world and the nature of the world. And every civilization has had its own creation myth as to how the world came into being, as long as there has been any form of written culture, and including, of course, religions. But nowadays, cosmology is generally regarded as being part of the domain of science. Indeed, it's part of physics. And that's because we now have a physical theory, namely general relativity theory, which enables us for the first time to have an actual description of the physical world based on the laws of physics as we know it. So people will now say that cosmology is a branch of physics. On the other hand, one has to realize that not all physicists, agree on what precisely the standard model of physics is. And certainly if you go outside the domain of physics, other people will disagree. People will say, well, the picture we have of physics from of the creation of the universe from physics is just another myth, and will eventually be overthrown, just like the myths of the Bible and any other traditions. I don't believe that. I do believe that our picture of cosmology today really is at least approaching the truth, although there's much we still don't understand. But I think what's interesting about the history of cosmology is that it tells us also about the nature of science itself. Because the way in which we've learnt about the universe is by using our instruments, our telescopes, to peer to ever greater and greater distances. And as we've done that, the nature of the universe has changed. The nature of the universe has obviously grown, but also our view of the nature of science has changed. And so I want to talk about cosmology from that perspective, about how cosmology has taught us about the changing nature of science. And in doing this, I'm not only going to be talking about cosmology, I'm going to be talking about the world of particle physics as well. Because obviously when you're studying cosmology, you're looking to ever bigger scales, but also science has looked to ever smaller scales in studying the nature of subatomic particles and quantum theory and things like that. And so really, when you're talking about cosmology, you're talking about both the outward journey to ever larger scales and the inner journey to ever smaller scales. And the reason they're connected is because we believe the universe is expanding and that it began with a Big Bang. But at the Big Bang, of course, the universe was very, very, very compressed. And so you can only understand what happened at the Big Bang by understanding particle physics at high energy. So you get this natural link between very small scales and the very larger scales at the Big Bang. So in some sense, you can think of the history of physics, if you like, as looking to ever smaller and ever larger scales. And cosmology, in some sense, envelops both of those activities. So maybe I should start off by saying a bit about the history of cosmology then, which is looking at the history of the larger scales.
Okay.
As you know, we started off with the geocentric view that the Earth is the center of the universe, and indeed essentially was the universe. But we know that view was overthrown by Copernicus when he realized that actually the center of the universe wasn't the Earth, but the Sun, and that the Earth goes around the Sun. And so that was the beginning of the heliocentric view. Of course, there was a battle, especially with the church, because the church didn't like us being dethroned from the center of the universe, but we all know that was the battle which the Copernicus eventually won. But then Galileo realized that our sun is just one of millions of stars that make up the Milky Way. And he realized there wasn't anything particularly unique about our sun. And very soon, of course, well, when I say very soon, we know, by certainly after a few hundred years, it was clear that, in fact, our sun is just one star which makes up what's called the Milky Way galaxy. The Milky Way is the band of light we see across the sky, but we're looking through the disk of the galaxy. And so the view for many years was that therefore the universe actually consisted of the galaxy. And for a long time, no one believed that there was anything outside the galaxy. But one thing I should point out is that getting even to the galactocentric view involved quite a big transition. Because, for example, even after it was realized that there were many other stars, the common view was that the domain of science would always be confined to the solar system. The famous philosopher Auguste Comte, for example, in the 19th century, he said that the domain of science will be forever confined to the solar system. Not because there was nothing outside the solar system, but because he thought there was no way we could ever understand it. But unfortunately, he was wrong, because a decade or so later they discovered spectroscopy, which is a way in which we were able to understand the composition of stars and get information of stars and their motions and things like that. So with the discovery of spectroscopy, the study of things outside the solar system, and indeed the whole galaxy, became the domain of legitimate science. But then when we get to the early years of the 20th century, the big debate was, is there anything outside the galaxy? And some people took the view that the galaxy was all there was. And indeed, even Einstein, when he had his theory of general relativity, thought the galaxy was the whole universe. But there were a few people who thought that there were actually some of the objects in the sky were actually what they called island nebulae outside our galaxy. And in fact, one of the people who first speculated about that was Kant, the famous philosopher. But this was controversial, and even there was a famous debate in the 1920s between two astronomers, Shapley and Curtis, as to whether there was anything outside our galaxy. And one side said that the things that appear to be outside our galaxy are really inside our galaxy. so that the galaxy is all there is. But the other side, Curtis, was arguing that actually they were outside our galaxy. Now, at that time, the debate was inconclusive, but the clinching evidence came really just towards the end of the 1920s when Edwin Hubble measured the distance of the Andromeda Galaxy, which is our nearest big neighbor, and proved that it was definitely outside our galaxy. He measured it by, he proved that by studying what are called Cepheid variables, and they have a periodicity in their luminosity, which gives you their distance. So he was able to prove that the Andromeda Galaxy is outside our galaxy. And that was a tremendously important discovery, because it meant it demolished the galactocentric view that our galaxy is the universe. But again, this transition didn't come easily. People had speculated about things outside the galaxy for a long time. But even, for example, Ernest Rutherford, the famous nuclear physicist, he said, early on in the 20th century, he was the head of the Cavendish Laboratory in Cambridge, and he said, I don't want anyone talking about the universe in my department, because they thought it was just idle speculation, which will ever be beyond science. But of course, Hubble proved him wrong. And Hubble not only proved that the Andromeda Galaxy was outside the Milky Way, he showed that actually there are millions of other galaxies, and which are at far, far greater distances than Andromeda. And now we know that actually you can study galaxies all the way out to the edge of the visible universe. When I say, let me first of all say what I mean by the visible universe. The other thing Hubble discovered was that not only are there these galaxies at great distances, he showed that the galaxies are receding with a velocity proportional to their distance. And the reason for that isn't because everything's running away from us. The reason for that is because space itself is expanding. So it's like having the surface of a balloon, and you imagine little dots on the surface of the balloon. If you blow up the balloon, all the dots move away from each other. So actually, this was even predicted by Einstein's theory of general relativity, although Einstein himself didn't realize it at the time, because he thought we were still living in a static universe. So the point was, though, that if the galaxies are all expanding, that means if you play the picture backwards in time, all the galaxies will eventually merge at a point. And that's what we mean by the Big Bang. And you can infer from the rate at which galaxies are expanding when the Big Bang occurred. And the timescale you get is roughly 14 billion years. So Hubble didn't know it that precisely, but we now know from the so-called Hubble Law of expansion that the universe began with a Big Bang 14 billion years ago. And that is what's called the cosmocentric view, because it's saying that that there are these billions of galaxies. But the point is, because the Big Bang began 14 billion years ago, light can only have traveled roughly 14 billion light years. So there's a limit to how far you can see. So when I talk about the size of the observable universe, I mean the distance light can have traveled from the Big Bang. And now we can essentially look back to the edge of the observable universe, and we can see galaxies. There are now 100 billion galaxies we can see. But when we look to very large distances, we're actually looking back in time. And because we're looking to great distances, but we're also looking back in time to when the universe was very, very small. So the point is, therefore, that we've progressed from the geocentric view to the heliocentric view to the galactic-centric view to the cosmocentric view. And that progress has not only made the universe bigger, but it has changed the nature of science, but also the domain of application for science. Because at every stage we're saying, the conservative people are saying, well, this is fine, but you can't take science beyond this domain, and then more data comes along and you find you can. Now, the current debate within cosmology is whether there is anything beyond the horizon. Remember, I was saying that there's the horizon beyond which you can't see. But there's no reason to think the universe itself stops at the horizon. It's just we can't see any further than that. It's rather like if you're on a boat, and you're looking to the horizon of the Earth. It doesn't mean that you can see to the edge of the ocean because the Earth is curved, but it doesn't mean there actually isn't anything beyond the horizon you can see. It just means that it's what you can't see, but it's there. And it's like that with the universe. No one would believe that the universe comes to an end at the horizon. It's just that we can't see it. However, a lot of astronomers may say, yes, but this is philosophy because if we can't see it, it's not part of proper science. It's not observational cosmology. But the trouble is, when people talk about things like the multiverse, they're saying, well, actually, there are parts of the universe which we can't perceive, and there may even be other universes which we can't perceive. And so now the big debate, and we talked about the reason for that in one of our previous discussions, arguments to do with the anthropic principle and the fine-tunings and things like that. So that's one reason some people like the multiverse. But the fact of the matter is that many models of physics, both from particle physics and cosmology, predict the existence of a multiverse. But the big debate is this part of science? Or is it just philosophy? Because people will say, well, if we can't observe it, it can't possibly be part of science, because science is based on observation and experimentation and things like that. However, other people will say it's not as simple as that. Other people will say there are many things in science we can't observe. I mean, we can't observe inside black holes. We can't observe quarks. I mean, we can't observe the Big Bang itself. But just because we can't see something doesn't mean it's not real. The question is, do you believe the theory which predicts it? And if the theory which predicts it can be confirmed, then you may believe in the prediction. But anyway, this is a big debate, and I myself take the view that there is a border between cosmology and what I call metacosmology, where in some sense physics merges with philosophy. One has to accept that if you don't have empirical evidence, for the time being, it doesn't qualify. It's not fully fledged science. But the point is, it's potentially science because it's potentially observable. And whereas it's true that at the moment we don't have any direct evidence for the multiverse, only theoretical implications, I would argue that you could potentially in the future have evidence for the multiverse. So that's why I call it metacosmology. So metacosmology to cosmology is rather like physics to metaphysics. And the point is, the whole history of cosmology, as I've sort of tried to describe with my brief introduction, is one in which yesterday's metacosmology becomes today's cosmology. Okay, so before Kant, the physics beyond the solar system was metacosmology, or at least metaphysics, if you like. Once they discovered spectroscopy, it became physics. Before Hubble had proven that these other galaxies were outside a Milky Way, speculations about things outside the galaxy were metaphysics, but then they became physics. And so in some sense, the whole history of cosmology is one in which metaphysical speculations ultimately become physically respectable. Indeed, the whole of cosmology might be regarded like that, because after all, we had cosmological models well before Einstein's general relativity, but one would have said they were philosophical rather than physical theories. Once we had the observations and indeed the theory, Einstein's theory of general relativity, it became respectable physics. So that's the point I'm trying to make. But the same story actually is found if you study the history of physics as it probes ever smaller scales. Because obviously we started off using our microscopes to study things, like ants and amoebas and things like that. And then we used more powerful things, electron microscopes, to study DNA structure and things like that. And then we had experiments to probe the nature of the atom. And then we have our accelerators like the Large Hadron Collider, which are exploring the nature of subatomic particles and getting to ever larger energies, because larger energy corresponds to smaller and smaller scales. But again, at every stage in this story, there have been skeptics. So, for example, we now know that matter is made of atoms. And we had atoms, the idea of atoms, it goes back to the Greeks, but also the idea of atoms, there was evidence from that from ideas of chemistry and thermodynamics. But for a long time in the 19th century, physicists were skeptical of the atomic theory because there was no direct evidence for it. But that all changed again in the 20th century because, well, Einstein's work on Brownian motion was evidence for atoms, and now, of course, we routinely probe atoms using experiments. But the point is, it was regarded as pure theory until we had the experiments. And then as we go to ever smaller scales, the same story arises. One has theories of the, for example, the unification of weak and electromagnetic forces. It was pure theory until the 1970s, when actually at CERN they did the experiments and discovered the W and the Z bosons, which confirmed that theory. And then later on, of course, only not so long ago, they discovered the Higgs particle, which was going up to even higher energy and confirming the standard model, so-called, of particle physics. But now we speculate with our theories about even higher energies. We speculate about the grand unified theories, where the strong and the weak and electric forces are unified. And we speculate about string theory and M theory, where all the forces of nature are going to be unified. But we still don't have energy for this. So again, there'll be the skeptics who will say, we shouldn't believe these theories because we don't have any direct evidence. I mean, M theory is all wonderful as a mathematical theory, but it's only mathematics because we don't have actual evidence for it from experiments. And that is true. But in my view, I hope that there will eventually be evidence for M theory, or at least some theory like that, because the history of physics is one in which people have always underestimated how far you can extend science. Whenever people say you can only take science this far, so far it's always proved to be wrong. We've always succeeded in taking it further. So I bet one day we will be able to extend science to test even things like M theory. We can't do it at the moment, but let's hope we can sometime. So you see, it's the same story when you look at the macro domain and the micro domain, that at the frontiers of science, be it on the macro level or the micro level, there is order. There is always this border between respectable physics and metaphysics, if you like, between science and philosophy. And that's the nature of things. And the more conservative physicists are always going to say, this isn't proper physics. And it's true at the time, there isn't direct evidence that it is proper physics. But the point is, if you wait long enough, the evidence has always come in, which has made it respectable physics. So I made a distinction between cosmology and metacosmology, and I think it's the same as observed in the microscopic journey. The border between at the frontier of science, the border between science and philosophy is always fuzzy and it's always changing. Now, that's interesting because I mentioned that the cosmology in some sense involves both the macro physics and the micro physics, because you're looking to ever larger distances, but when you're thinking about the Big Bang, you're looking back to ever earlier times when you've got higher and higher energies involved. Now, what's interesting is that when you get to the Big Bang, the very large meets the very small. I talked in one of our previous discussions about the cosmic Ouroboros, you remember, which has all the different scales of structure in the universe. And you may remember in that diagram the head meets the tail at the Big Bang. And the reason for that is because when you look back to very large distance, when you look at very large distances, you're looking back in time because light travels at a finite speed. And so when you look back to 14 billion light years, you're looking back to when the universe was very, very, very tiny. That's why the very large meets the very small. Now, to me, there is an interesting question, and this is as follows. In some sense, you've got the macroscopic frontier between physics and philosophy. And on the microscopic level, you've also got the microscopic frontier. So if you like, you've got the multiverse at the macroscopic frontier, because that's what people currently argue about. And you've got M theory at the microscopic frontier. But what's really interesting to me is that these two frontiers meet at the top of the Ouroboros. Okay? And so then you can ask the question, what does this mean? Is this the end of science? In other words, has physics gone as far as it can go? Because this is where the very large meets the very small. In other words, is the Big Bang represent the completion of our knowledge? Or does it merely represent a transformation in the nature of science? Now, I am going to argue that it represents not the end of science, but it represents a transformation in the nature of science. You see, what is going to happen, I should say, at that top, where the very large meets the very small, that's our final theory of physics. It's the theory of everything. It's the theory of quantum gravity. It's where general relativity meets quantum theory, which I think I've talked about before. So the question is, when we've got our final theory, is that the end of the journey as far as physics is concerned? Is science complete? I'm not making a clear distinction between physics and science here, but I'm primarily talking as a physicist. But the question is physics complete? Well, I would argue that it isn't. I would argue that this merely means a transformation in the nature of science. You see, I've talked about the history of cosmology, how we've gone from the geocentric to the heliocentric to the galactic-centric to the cosmocentric view. Well, what is next? I've already intimated to you in our previous conversation that I think higher dimensions are really crucial. And those higher dimensions come in at the top of the Ouroboros, where you've got your final theory of physics. And as you know, my own model, which is not the mainstream physics model, is that this final theory, this marriage of relativity and quantum theory, in some sense is going to accommodate mind. And so, because I'm wanting to regard that as part of science, I will argue that when you get to the Ouroboros, this is merely a new paradigm in the nature of science. That you're going beyond the simple physicalistic or materialistic view. So if you like, I'm saying the next stage, after you've gone through from the cosmocentric view, the next stage, if you like, is to get over the matter-centric view. The matter-centric view saying that the matter is all there is. Now, of course, the skeptic will say you can't, because science studies matter, and therefore, if you go beyond matter, it's not part of science. But again, I disagree with that, because history has told us you've got all these paradigm shifts, and so I don't see why the next paradigm shift shouldn't be one that goes beyond the matter-centric view. And of course, when I say that, I'm talking about a vision of science which accommodates mental phenomena. But to me, the fascinating thing is that this is involving both macroscopic and microphysics and macrophysics. But of course, that is just my speculation. So that's how, in this discussion, we're not talking much about mind and parapsychology and things like that. But ultimately, that's, to me, where the link comes. Because the link comes when you get to the top of your Ouroboros. That is where, from my perspective, mind is going to enter the picture, and even where spirit is going to enter the picture, if you want to talk in those terms. You see, physicists always say, people always say, you got a theory of the Big Bang. And almost everyone now will accept that as you go back in time, the universe becomes more and more compressed. That's the standard view. But then the skeptic will say, well, that's fine. But the point is, you still can't answer the question, what happened at the Big Bang itself? Okay? So at some stage, physics is going to break down. And so, for example, when we discovered the evidence of the Big Bang from the microwave background radiation, the Pope wanted to say that this was evidence for Genesis, because Genesis said the universe, the idea of the Big Bang was reminiscent of the account, I suppose, of Genesis, let there be light and all that. But then Lemaitre, who was both a priest and a cosmologist, warned the Pope not to say that, because it was a very dangerous thing to say, because to say that physics cannot explain the Big Bang is just an assumption. It is true that the closer you go back to the beginning, the more speculative the physics becomes. And you can always say that the physicist can never actually ask what happened at t equals 0. Okay. And so the Pope might have said, then you're in the domain of theology. You've got to ask who lit the fuse. On the other hand, someone like my supervisor, Stephen Hawking, would say, no, that's not true, because it's true that current physics breaks down at the Big Bang. Classical relativity breaks down. But we have people like Stephen Hawking who speculate about quantum cosmology, which is precisely trying to explain the origin of the universe using not just quantum theory, but the theory of quantum gravity. And they've had some success. So someone like Stephen Hawking would have claimed that physics can explain what happened at the beginning of the universe, and that furthermore, there's no need for a God, because in some sense the universe can create itself. Now, of course, not everybody would agree with Stephen Hawking about that. I actually don't agree with it myself. But nevertheless, it's very dangerous to simply assume that you have to go beyond physics when you get to the Big Bang. Because although in the old days people would have said that physics can't explain the Big Bang itself, it can't explain what happens at t equals 0, now physicists are trying to do that. In other words, the final theory of physics does address the question of what happens at the Big Bang. But my own view is that actually when you get to the beginning of the universe, this is when you're in the domain of mind. Because if you believe mind is to do with what happens at the top of the Ouroboros, that in some sense is saying that mind was there first, because in this higher dimensional picture I spoke about before, mind is associated with this higher dimensional space, of which the physical world is just a lower dimensional slice. So in some sense, when you ask what happened before the Big Bang, the answer will be, in my approach, that actually there was this mind. In some sense, there was mind, because it was that. And so out of this mind with a capital M, of course, out of this mental space that became the physical space. Well, of course, I'm not saying that's the correct picture, and philosophers will have argued about that for a long time. But the question is, which is primary, matter or mind? And as you know, there are many philosophical viewpoints on that. In some sense, I guess I'm saying that mind is more fundamental, or at least matter and mind are two sides of the same coin. As you know from our previous discussions, I take the view that mind is not secondary, that mind at least has equal ontological status to matter. And so that is my own particular view. So that's a rather long answer to your question about the nature of cosmology, but I've tried to use this to illustrate the fact that the history of cosmology is also something about the history of science. You see, you can ask, what is the nature of science? Okay, because there's no clear-cut answer to what the nature of science is. For example, you might say science involves experiments. And of course, originally it did involve experiments. But when you talk about astronomy, you can't do experiments with stars or galaxies. All you can do is observe the universe. And we observe billions of stars and billions of galaxies, and that's instead of doing experiments. So in some sense, the idea that science is based on experiments doesn't work. Not if you're going to regard astronomy as a part of science. Now, when you talk about the universe, you're in even a worse state, because there's only one universe. At least you've got billions of stars, so you don't have to do experiments on stars, because you can watch billions of stars in different stages of evolution. There's only one universe. So you might say, well, therefore the universe isn't part of science either, because you'd need lots of universes. But on the other hand, it's now accepted that you can study the universe as part of science. So even observations don't seem to be the key feature of science. Other people will say, well, the crucial feature of science is that you have to be able to test ideas. You have to be able to falsify ideas. And that seems fair enough. And for example, that's why people will say they don't think the multiverse is part of science, because you can't falsify it. You can't see these other universes, so how can you falsify it? But that may be wrong too, because the question is, how long does it take to falsify an idea? You see, I mean, if we take M theory, it might take 100 years to solve the equations of M theory and prove or disprove them. But does that mean it's not part of science? I mean, just because you have to wait 100 years to prove something, I don't think necessarily you should say it's not part of science. You can say it's science in waiting, if you like, rather like metacosmology. And so I think, in fact, Steven Weinberg, who's a very great physicist, he contributed to my volume on universe or multiverse, and he made a very interesting remark, which I'm not going to quote verbatim, but he says the history of science is not just a matter of our changing view of nature, it's our changing view of the nature of science. And now, bear in mind that Steven Weinberg would be completely skeptical of many of the ideas I'm talking about when I talk about consciousness and mind. But nevertheless, I think that's a very profound remark, in general, that the nature of science changes. And so you see, this is relevant to a subject like parapsychology, because when people say it cannot be part of science, consciousness cannot be part of science, let alone paranormal phenomena, they're making an assumption about the nature of science, that the nature of science will always be as it is now. And I just don't believe that. I think the nature of science will change. I think eventually science will have to expand to accommodate, if you like, the first person perspective. It will have to accommodate consciousness and mental experience. I may be wrong, but at least that's the assumption on which I've been working most of my life.
It strikes me, Bernard, that the multiverse theory or hypothesis that developed largely because people were favoring it rather than introduce consciousness then and there as an answer, for example, to the issue of the fine-tuning of the universe that led to the anthropic principle. So multiple universes seem more attractive than consciousness, but what you're suggesting is you can't really avoid the problem of consciousness. You can only kick it down the road a little further. Sooner or later, it's going to come back and bite you.
I would say that. I mean, I think in a previous discussion, I talked about the problem of whether you choose, with the fine-tunings, whether you're going to explain them with the multiverse or God. And so in some sense, you when faced with the choice of choosing a multiverse or God, most physicists would prefer the multiverse, obviously. I mean, many physicists would prefer neither of them. But there's a large number of respectable physicists who would prefer the multiverse to explain the fine-tunings. Although that's not the reason for invoking the multiverse. The multiverse is predicted by theories of cosmology and theories of particle physics. But if it's there, it may explain the fine-tuning. Now, that's somewhat different, though, from the question of the relationship of the multiverse to consciousness, which you just raised. I would say, I mean, there is a link between the consciousness and multiverse. One of the reasons for invoking the multiverse is the many worlds interpretation of quantum theory by Hugh Everett. So there is a link conceptually between that sort of multiverse and consciousness. But I would say that the link between consciousness and the multiverse is not definite. I mean, the question is, what is the fine-tuning for? If you believe the fine-tuning is for consciousness, in other words, the universe is fine-tuned for consciousness, then you might want indeed to say there's a link between the idea of the multiverse and the idea of the consciousness. Okay, in the sense that the consciousness only exists in a particular some small subset of all the possible universes. But on the other hand, not everybody would take that perspective, so it's not completely clear. But to me, I mean, the question is there consciousness in all the multiverses? And of course, we don't know the answer to that, and so that's still just speculation. Now, so far, I mean, I've just talked about cosmology. I think I could also talk a little bit about black holes, because in some sense you have much the same story about black holes as you have about cosmology. I mean, we now know that black holes are a prediction of Einstein's theory of relativity. We've known that since 1916, in fact, when Schwarzschild discovered the solution from Einstein's equations of general relativity corresponding to a black hole. And as I explained in a previous discussion, there was no evidence for this for about another 50 years. And so, and Einstein himself didn't believe in black holes. However, in the 60s, we discovered evidence for black holes. And now, of course, we have overwhelming evidence that black holes form as a result of stellar collapse. We got evidence from gravitational waves, from the mergers of black holes, from the LIGO Virgo project. And not only that, but we know that there are, on bigger scales, we have bigger stars, so-called we may have intermediate mass black holes, which have got masses of maybe 1,000 or 10,000 solar masses. And then when we go on larger scales beyond that, we know in the center of galaxies we have what are called supermassive black holes, which have a mass anything from 1 million solar masses all the way up to something nearly 100 billion solar masses, 10 to the 11th. I mean, we're now up to something like 4 times 10 to the 10th solar masses. So it's an incredible range of masses. Now, of course, you notice that you're going to ever larger scales. And historically, again, they've been skeptical about black holes as you go to bigger scales, because even at first people were skeptical about stellar black holes. I mentioned that Einstein didn't believe in them, and nor did Eddington. Then there was evidence for that, but then people were very skeptical about having the larger so-called intermediate mass black holes, but then the evidence for that has only come about relatively recently in the last few decades. And then the idea that there were big black holes in the centers of galaxies was also regarded as even more speculative until about 30 years ago. But now the evidence is overwhelming. So nearly all astrophysicists will accept that there are these big black holes in galaxies, in the centers of galaxies. And there's a certain sense in which the whole universe is a black hole, but in a way I won't go into. It's a little bit technical. So in other words, the history of black hole physics is looking to ever larger scales. And again, at every stage, the more skeptical physicist is saying, I don't believe in these black holes, I only believe in the stellar ones, I don't believe in the intermediate ones, or I believe in the intermediate, I don't believe in the supermassive. The history of black hole physics is going to ever larger scales and finding ever larger black holes. It's just like the story of cosmology. Now, furthermore, we're talking about what are called macroscopic black holes, but also there is the possibility that little black holes formed in the early universe, these are primordial black holes, which I think I talked about in our first interview. And these smaller black holes, again, there isn't direct evidence for them, they're pure speculation, but nevertheless, they're tremendously interesting because we know the ones which are sufficiently small evaporate through Hawking radiation. They have to be less than 10 to the 15 grams. That's something like the mass of a mountain, but it's the size of a proton. And then they evaporate due to these quantum effects. Well, people may say, well, we don't believe in these primordial black holes, but nevertheless, most people believe in Hawking radiation. So, and Hawking only discovered Hawking radiation because he was thinking about primordial black holes. So, I personally think that primordial black holes may well have formed. I spent 40 years working on it. I don't know for sure whether it's a valid scenario, but at least I think the evidence is becoming stronger. Some people think that the dark matter could even be primordial black holes. But also, when we get to the smallest scale of all, even smaller than the Hawking mass black holes, you get to black holes of the Planck mass. Now, the Planck scale is the scale associated with quantum gravity, where relativity meets quantum theory. And the Planck scale is something like 10 to the minus 5 grams, okay, which is about, I suppose, the mass of a flea or something. No, mass of a grain of sand. And the size is 10 to the minus 33 centimeters, incredibly small, the smallest scale you can ever have. It's the smallest scale in which space can be treated as a continuum. But the point is, it's clear that these Planck mass black holes are going to play a crucial role in our final theory of quantum gravity. But you see, the point is, as physicists think about these smaller black holes, again, it becomes ever more speculative. And people say, well, we still don't have evidence for Hawking radiation, even though everyone tends to believe in it. There's no evidence for it. And other people say, we certainly don't have any evidence or knowledge about Planck mass black holes, so that's even more speculative. So again, it's the same story as we got from cosmology. When you look to bigger and smaller scales, you seem to find black holes everywhere. But again, it becomes more and more speculative. And of course, until we've discovered these small black holes, for example, you might discover a small black hole in the Large Hadron Collider, but until we've discovered it, it just becomes, if you like, metaphysics rather than physics. But the point I'm saying is that the study of black holes, the history of the study of black holes, is really the same story as the history of cosmology. They both involve the idea that you look to ever smaller and larger scales. They both involve the idea that you always encounter this skepticism about whether this is respectable physics. But with time, you find the skepticism breaks down because you discover there are these ever bigger and ever smaller black holes. And I must confess now, I see black holes everywhere. I'm obsessed with black holes. So if you take this lovely Ouroboros picture, which previously we used to describe all the scales of structure in the universe, subatomic, all the way up to galaxies and the universe itself, you can also put black holes around this figure, this cosmic Ouroboros, and you have very small Planck mass black holes at the top left on the macroscopic scale, and you get the universe as a black hole in some sense at the top right. And so I can also use this cosmic Ouroboros to represent all the different types of black holes in nature. Because to me, black holes essentially, I see black holes everywhere. And that's because I work on black holes, but I think it's also true. This is one of the discoveries of physics, that black holes really do play a fundamental role in physics. One of the reasons that Hawking's theory of radiation of black holes was so important was that it unified three areas of physics. It unified relativity theory, quantum theory, and thermodynamics. And that's what made it such a beautiful idea, even though we still don't have any definite evidence for Hawking radiation. Almost all physicists believe it because it's such a beautiful idea. It unifies these three different areas of physics. And the great physicist John Wheeler, who actually coined the word black hole I was speaking to him shortly after Hawking made his discovery, and he said, just talking about Hawking's theory is like rolling candy on the tongue, because it's so beautiful even to talk about it. And I tend to agree with that. It's a beautiful idea. So anyway, I've talked about how both cosmology and black holes, in some sense, tell the same story. That science is forever expanding its frontiers on the largest and smallest scales. And that's where I think the link with the more speculative topics come from.
Well, we're dealing with the question of the limits of science itself. And the case of Hawking, who was your mentor and faculty advisor when you were at graduate school, is interesting. He's regarded, I think, today as one of the greatest physicists of the last 100 years. And yet, at the same time, according to what you've told me, I have to think that some conservative physicists might say, oh, he's just doing mathematics and philosophy. He's not doing real physics at all because we haven't ever observed Hawking radiation.
That's an interesting point because you see, most people would say that Stephen's greatest discovery was the discovery of Hawking radiation. But since it hasn't been observed experimentally, some people will say it doesn't count as a proper physical discovery. And that's why he never got the Nobel Prize for that, because he would only have got the Nobel Prize if they had got evidence for Hawking radiation. Even though it's such a beautiful idea, and even though everyone accepts it's fundamental, one of the most important discoveries of the 20th century physics, nevertheless, there's no evidence for it, so it didn't qualify for a Nobel Prize. Other areas Stephen has worked in are also, for example, he's famous for the singularity theorems. His first work was to prove the universe started with a singularity, which is merely a point where all physics breaks down. The density gets very high at the Big Bang, basically, and all known physics breaks down, including relativity theory. So relativity theory predicts its own downfall because it predicts there are endpoints in space-time. The same is true in a black hole. There are singularities in the centers of black holes where physics breaks down, relativity theory itself breaks down. So it was Penrose who discovered there were singularities in black holes, and Hawking and Penrose who discovered that there were singularities in the universe, in the cosmological context. But again, you could argue that that is a mathematical rather than a physical theory, because actually you can't physically prove. No one's going to observe proof of the singularity theory, the singularity theorem, because we know physics itself is going to be replaced by some other theory like quantum gravity. So it is true that some of Stephen's discoveries have not been proven. For example, a lot of his work in later years was to do with quantum cosmology, and it's very hard at the moment to have actual direct evidence for these quantum cosmological models. It's rather like M theory. We have the mathematics, we can try and solve the equations, but we don't yet have definite evidence for it. It may be true because it's a beautiful theory of physics, but we don't have the actual evidence. So you could argue that Stephen himself was working on what was the border between straightforward, respectable physics in the sense that you can directly verify it, and if you like, metaphysics, where it's in the domain of mathematics. As I said, M theory, some people would regard that as metaphysics, as mathematics rather than direct physics. But I still think eventually it will become part of respectable physics. It's just in purgatory until we've discovered it. Like Hawking radiation. I do like to think one day we're going to discover Hawking radiation, sadly not in his lifetime. But until we discover it, it's in the sort of purgatory of physics, because we haven't got the evidence for it. But it is interesting, though, because Stephen, I did my PhD with him, and you refer to him being one of the greatest physicists of the last 100 years. You have to be careful when you get into these sorts of discussions, because people always ask me, where does Hawking stand in the great pantheon of physicists? Was he an Einstein? Was he a Newton? He was portrayed, by the media as being another Newton and all this. Stephen himself would never say that, because obviously that there is a lot of press hype. But then people say, well, how great a physicist was Stephen? To me, he was certainly the smartest person I ever knew. Okay, and I regard him as one of the greatest. Well, one of the greatest physicists. But then, of course, there are a lot of great physicists too. There are all the people like Weinberg and Feynman and Hooft and all these people. They're all brilliant physicists, and I think it's rather silly to get into the question of who is the greatest physicist, because they've been dozens of great physicists, and sometimes people go to the opposite extreme and they will say, no, Stephen wasn't such a great physicist, he's just been built up by the press because he was disabled and he's become an iconic figure, but really he wasn't one of the great physicists because he never got the Nobel Prize. And I think that view is wrong as well, because he really was a great physicist, there's no doubt about it, and he would have been a great physicist even if he hadn't been disabled. It is true that because of his disability, because he was locked into his wheelchair, he became an iconic figure, and there's no doubt that was part of the reason he was so famous. But people who say that he wasn't a great physicist, I mean, I get very annoyed at that, because he certainly was one of the great physicists. But, when you get into the question of, was he in the top 10 of the 20th century, it becomes a bit silly, because, you can't line up physicists like Olympic runners and say who was the top, because there are different ways of being a great physicist. There's some really smart people who never publish papers. There are some people who publish lots of papers who aren't as smart, and there are different ways of being smart. All I can say is I worked with Stephen for 5 years or so, and he was my friend for much longer than that, but he was certainly the smartest person I ever met. I mean, in the sense that I would talking to Stephen, I mean, I would get such insights, and I would get more help talking to Stephen for a few minutes than I would get talking to most people for weeks and talking to myself for months. I mean, he was just very smart, and there's no doubt about that. But there are also lots of other smart physicists as well. And of course, I don't know how much you want me to say about Stephen, but I did my PhD with him, and I was very lucky, because he, I was working with him at the time he discovered Hawking radiation, and I got to work on primordial black holes, so it got my career off to a good start. But I didn't have the normal sort of relationship, I didn't have the normal supervisor-pupil sort of relationship with Stephen, because he was disabled. He was already in a wheelchair, and so I would spend a lot of time with him. I would share an office with him. We were in America, I lived in the house with his family. I used to travel around the world, going to conferences and collecting medals with him and things like that. I mean, he was getting the medals, I was just accompanying him. So my relationship with Stephen was more intimate than you would have the normal relationship between a student and a supervisor, but it was. I'm very grateful for that, because it was a tremendous privilege to sort of work with someone who was so smart, and indeed to count him as one of my friends.
I suppose it's fair to say that he would be one of the physicists who had very little tolerance for your explorations in consciousness and psychical research and so on.
That is true. And so although I have tremendous admiration for Stephen as a physicist, we certainly didn't see eye to eye on some of those topics. He did, as a teenager, he did actually read, he read Ryan's books. So he did have an initial interest in parapsychology experiments, but I think he soon concluded that there was no evidence, that he soon dismissed that. He knew I was interested in the subject. And so that was on parapsychology. Though oddly enough, and I never tried to persuade him otherwise. I mean, he knew I was interested in the subject, but I didn't try and sort of persuade him otherwise. But on the other hand, there were some interesting stories. I remember, for example, on one occasion, I was stuck on some equations, and I had a dream, and in the dream, I met Stephen, and Stephen told me how to solve the equation. And I woke up and I checked it, and that was true. I could solve the equation. I was able to solve the equation. Well, of course, I saw Stephen the next day, and I said, Stephen, in my dream, you told me how to solve the equation. Well, of course, Stephen laughed because he didn't believe, and the implication being maybe I picked this up telepathically. Well, of course, Stephen laughed because he didn't believe any of that at all. And he didn't believe in telepathy at all. And the way I tell the story, I normally say, so I said, right, Stephen, you're not on the paper. However, to be honest, although I tell that version of the story, I don't think it can be true, because I don't think I was too much in awe of Stephen to say something like that to him. But I did have a dream in any case. You know, it's hard, after 40 years, you can't quite remember what was true and what was in your mind, but I certainly had the dream. And again, I'm not claiming that was evidence of telepathy, of course I'm not, but nevertheless, an interesting little story about how there was this difference of opinion. In fact, even my very first encounter with Stephen involved an amusing coincidence. Stephen was attending a meeting at Les Ouches in France in 1972 on black holes, and I was not able to attend the meeting. I was about to start my PhD. I was too junior. I was doing a course at CERN for students studying particle physics in Geneva, which is quite close to Les Ouches. And there wasn't room for me in this study, in this course. But however, there was a 1 week, there was a space. And Stephen sent me a message by a friend that I could attend for 1 week. So I left CERN and I went off to Les Ouches. And I turned up and met Stephen and his family for the first time, attended the lectures. This was the first ever big meeting on black holes, so it was actually quite an interesting meeting in itself. Stephen assumed I was there because he'd invited me, but actually I was just there because I'd randomly decided this was a good time to turn up. And what happened was, at the end of the week, the person who was supposed to have delivered the message telling me that I was invited, turned up at the conference and apologized for not delivering the message. And only at that time did Stephen realize that it was just a coincidence that I turned up at the week I was invited. Well, I'm not saying that's evidence for anything psychic, but it was an interesting coincidence. And as you know, I've always been fascinated in synchronicity. So in some sense, my whole career with Stephen started with that synchronicity. But you're right, Stephen was very skeptical about of Psi. He was also very had an antipathy towards philosophers, and certainly had an antipathy towards theologians. But again, I mean, I disagree with that. I mean, you have, as I said, it's a bit ironic because in some sense Stephen was working in areas which were on the border between, if you might like, between physics and metaphysics. Some of the things he was working on were in the sort of because there wasn't direct evidence for them, might be regarded as being in a little bit beyond the borders of conventional physics. But I never shared Stephen's disdain of philosophy, mainly because, as I've explained, I see there as being this natural border between physics and philosophy. Physics had its birth, science had its birth in natural philosophy. And so, and also I didn't share Stephen's disdain of ideas of spirituality. I mean, Stephen wasn't interested in things like, he didn't believe in God, certainly, and as I indicated before, Stephen thought the universe could explain itself. He co-wrote this book, The Universe in a Nutshell, which is basically saying the universe can explain itself. You don't need anything outside physics. There is this famous phrase in his book, Brief History of Time, about knowing the mind of God, for example. But I think everyone accepts that he said that tongue-in-cheek. Stephen didn't really believe in God. In fact, it's rather ironic because Stephen was blessed by 3 popes, and he's ended up in Westminster Abbey with his ashes interred next to Isaac Newton. So if there is a God and if there's a heaven, Stephen's obviously got a good references. Nevertheless, I know Stephen himself didn't believe in God, and so he didn't share my interest in in spirituality in any sense. And people used to say to me, well, why didn't you try and persuade Stephen to get interested in these things? Why didn't you try and make him more spiritual? And I always took the view, I don't want to. I mean, because Stephen was supremely gifted as a physicist. Okay, his role in life was to grapple with the problems of physics, and it wasn't to get involved in psychic experiences and meditating and having mystical experiences. That wasn't his way in life. I mean, the world needs scientifically enlightened people and it needs mystically enlightened people. But there's no reason why one person should be both. And I think it would have been wrong to distract Stephen from his path. His path was to use his superb intellect as a physicist to understand the universe. And I had no desire for him to spend his life joining me in any sort of mystical expedition. I mean, I think if Stephen had spent his life meditating, sitting in his wheelchair, meditating, trying to become one with God, I think it would have been a tremendous waste for physics. So it didn't bother me at all that Stephen didn't share my views, and I never tried to persuade him otherwise. I've never felt a desire to actually persuade my physics colleagues that they should be interested in conscious and psychical research. People should do what they're good at. But there is an interesting point here, Jeff, and that is, it is a bit disconcerting sometimes because, as you know, one of my passions is also psychical research and trying to understand psychic phenomena. And I know most of my physics colleagues, including Stephen, were completely skeptical about these phenomena. And indeed, not only Stephen, but some of the smartest people I know share his skepticism. And that does bother me sometimes, because we had a discussion once about belief and whether one believes in something. And I find with myself that I'm quite impressionable. And my belief does tend to be affected by the beliefs of the people I'm mixing with. So although, if you ask me, I do have a belief, I assign a high probability to some of these phenomena, it does worry me when nearly most of my physics colleagues don't share that belief. And, spending half my life, probably more than half my life, with people who think that psi doesn't exist, and then another half of my life with people who take it for granted, it's a little bit disconcerting and it's confusing. And I find that if I'm spending a lot of my time with the skeptical physics colleagues, I then question myself. I start saying, well, maybe they're right. Maybe these things don't exist. Maybe I'm deluding myself. But then I go and spend time with my psychical friends, and then I change my mind again and think, of course this is right. But the point is, for me at least, maybe I'm just very impressionable. My belief tends to... I'm swayed by what my colleagues are saying. So it does bother me when people like Stephen, who I so admire, disbelieve these phenomena. And it's not just Stephen. I mean, a lot of the great physicists who I admire so much will also share this. I mean, there are many great physicists someone like 't Hooft, for example, who played a key role in the final unified theory of physics. He says psi is he doesn't believe in psi. And it's a complete fallacy to say that physics can ever explain it. Feynman, for example, when I went to Caltech with Stephen, we got to know Feynman quite well. He would come and visit Stephen in the office, and Feynman was my hero. He was like a godlike figure in Caltech. Feynman was probably even smarter than Stephen. He was one of the greatest physicists of the 20th century. And it was so exciting going to Caltech to get to meet Feynman. And in fact, one of my great moments is when Stephen gave his first talk on black hole radiation. Feynman was in the audience and I was at the front helping Stephen show his slides. And afterwards I learned that Feynman had drawn my portrait. He used to like drawing pictures. And during the seminar, he was sitting in the front row and he drew my picture. And so I was excited by that. And I rung up his secretary and said, look, can you get hold of Feynman's note? Because he drew my picture. Well, it turned out that it was on the back of an envelope and he'd thrown the envelope into the garbage bin. But I asked the secretary to get it for me, and she retrieved this envelope from the garbage bin. And this envelope, it's got my picture in the middle, and then it's got notes on Stephen's talk, first talk on Hawking radiation and around it, and then it's got some Feynman diagrams. Well, today I've still got that envelope, and it's framed, and it's one of my most valuable possessions, because Feynman was like a hero to me. And yet the point I was going to make was Feynman too was completely skeptical of psychic phenomena. And I once got into an argument with Feynman because we attended a talk on telepathy at Caltech, and after this talk I started discussing some issue about whether there was any evidence for telepathy falling off with distance. And Feynman got very annoyed, and he said, "What you mean? It's meaningless to talk about whether it falls off with distance because it doesn't exist." So the point was, you can have great respect for someone but still disagree with them. And so the question is, I sometimes ask myself, how come all these smart people, most of whom are smarter than me, how come they don't believe in these phenomena and I do? Well, I managed to convince myself that the reason is simply because they haven't had the experiences. They're much more focused on, well, whatever, left brain activity, if you like, than right brain activity or whatever. I've also realized that smart people are like lawyers. They can argue for whatever they want. So if you don't believe in something, you convince yourself that, because you're smart, that it doesn't exist. So I decided that being smart was no guarantee that you were right, because if you're smart, it just means you convince yourself that what you happen to have the belief you happen to have a propensity for is correct. So at least I hope it's not true that because these people are smarter than me that they're correct. I hope I'm right about that. But to me, it's always a fascinating, when you're talking about the nature of science and the question of whether science will accommodate these phenomena. The first thing you've got to decide is, are the phenomena real? And then if they're real, will science expand to accommodate them? And to me, it is fascinating. The sociology of it is fascinating.
Well, I am under the impression, Bernard, that even though these people disagreed with you, that it wasn't an impediment to your career, that you also maintained a public profile as past president or president of the Society for Psychical Research. They still respected you as a physicist, and I'm assuming they didn't necessarily try to dissuade you from pursuing these interests.
Well, the point was, during my career as a physicist, I tended to be quite discreet about my interest in parapsychology, and certainly also about my interest in spiritual matters. And so I wouldn't talk about it very much. I mean, I would never publish any papers in physics journals about this. Indeed, I wouldn't have been able to publish in physics journals the sorts of ideas like I talked about with you in the last discussion, hyperspatial models. I could never publish that in a physics journal. It's just too speculative. Now, of course, my friends knew about this. I mean, Stephen Hawking would know about it. And so my close friends knew I was interested in these phenomena. But I don't think it was particularly well known to the general physics community, because I just knew from observation that if you express an interest in these topics, it can be an impediment to your career. I mean, even to be interested in psychical research could block your promotion, could even lose you a job. So I think people, my friends, would merely tolerate it and say, well, yeah, okay, he's eccentric, he's got these strange views, we don't follow them, but that's fine. Everyone's got their eccentricities. I think there are some people who probably did disapprove of me rather strongly, being interested in these things, because there's no doubt that physicists who take an interest in these subjects, let alone believe in them, it can result in antagonism. Now, the point was, though, that later on in my career, I had to play a higher profile. When I became the president of the Society for Psychical Research, one of my duties, of course, was to put my head above the parapet. And so, in some sense, I came out at that stage, and was more public. But even then, I was relatively discreet in what I said. So, you won't find so many attacks. Normally if you're interested in the subject, you're going to be attacked by a lot of the skeptics, and you'll be attacked in Wikipedia and all things like that. I seem to be quite lucky in avoiding that, but I think that may just have been because I was a little bit, kept a low profile. Now, I've now recently retired, and I now feel I'm out of the danger zone in the sense that I can't lose my job. So I'm becoming a little bit more open. In fact, even my interviews with you could be a reflection of that, because I don't think I've got much to lose, in the sense that I'm not going to, I suppose I could lose my reputation, but I'm not going to lose my job over it. Now, I think some of my friends some of my physics colleagues will say, oh, well, he's retired. Obviously, like a lot of old physicists, he's just become, a bit soft in the head. And it's just a result of retirement. But of course, my friends know I've been interested in these matters all my life. So that isn't the reason. If I was soft in the head, I was soft in the head from the beginning. But it's an interesting issue to what extent one should be open about this, because I think I told you that I was always advised to make my career in a respectable field before I started becoming more open about this. And that was, in some sense, my policy. I've now become more open about it. But it's interesting. I think the subject, psychical research, will become more respectable as more and more eminent people say you should listen to this, because by and large, what determines what is respectable in science is actually a function of just a few key people. You only need a dozen key people to say this is respectable, and it becomes respectable. Like the anthropic principle, which was regarded as a taboo until a few dozen eminent physicists said this is respectable. I think it's the same as psychical research. I mean, it will only need a few respectable physicists to start saying we should take this seriously. And I think the mood may change, and it may become respectable. But the way in which this transition occurs is very subtle, and it takes a long time. And certainly there's no guarantee it will occur in my lifetime. Because I was talking earlier about the border between physics and metaphysics, okay, and it's exactly the same. I mean, when you're talking about psychical research, that too is the border between science and philosophy. In fact, in a way, that's the reason I was talking about black holes and cosmology, because I'm saying even those areas can be regarded as being the evolving border between physics and metaphysics. Similarly with psychical research, there's no doubt at the moment that psychical research is out of respectable science, and it's out. It's not regarded as respectable. But nevertheless, I still believe that eventually it will become the domain of respectable science. So all the time I was arguing that the domain of respectable science is evolving. The hidden message, if you like, is that psychical research may also become part of that, the respectable arena of science. Now, I'm talking about psychical research. I've not been talking about spirituality, which is my third interest. In some sense, it's easier to be spiritual and scientific because there are quite a lot of religious scientists who believe in God, for example, and they're scientists, and they just make a clear division between their scientific life and their religious life. So they go to the laboratory on weekdays, they go to church on Sundays, and in some sense, they're sort of non-overlapping magisteria. So in some sense, they're two separate parts of life. And therefore, physicists can be a bit tolerant if you merely have mystical experiences or if you're interested in religion. The problem is with psychical research is that psychical research is making the link between the science and religion. And that's why it's such a contentious area. So a parapsychologist will come under much more attack from a scientist than someone who's merely spiritual. The point I would like to make is that this extended science, to me, has got to accommodate not only mind, I feel it also has to accommodate spirituality. I mean, obviously, spirituality is a rather vague term. And that's why I talked in my very first interview about how I'm interested in science, psychical research, and religion. To me, one wants to link all three of these areas. And so I want a theory of physics, if you like, which is going to accommodate all of them. Normal, paranormal, and indeed transpersonal or mystical experience. And that is the challenge. And the point is, I think once you start accepting that mind is an important part of nature, that's just the first step on the slippery slope to spirit. Okay? Because, I mean, if you're going to say mind is important, which is in some sense the main point I suppose I was making in my third interview with these hyperspatial models, you're then more or less got to start saying, well, maybe spirit is important as well. And then you get into thorny issues like the nature of God and cosmic consciousness and things like that. So I hope at least that over these series of discussions, I've explained why I feel it's so important to have an all-embracing paradigm, which is going to accommodate all three of these areas. But it's not just a matter of having an intellectual theory which accomplishes this. It's also the interesting issue, in some sense, from a historical, sociological point of view, how the nature of science must change in order to do that. And maybe that's the point at which I should end, that I do believe the nature of science is going to change.
I would agree with you. I think it may take hundreds of years, but eventually I would expect we'll see a merging of what you're calling metacosmology and theology and conventional physics. At some point, they'll all come together. That would be a grand unified theory.
But I don't know what the timescale is going to be, Jeff, because it's so hard to. I mean, the amazing thing is that after just a few hundred years, we're already apparently close to a theory of everything, at least in physics, which is really fairly remarkable. You know, that in just a few hundred years we've come to that point. Now, as I've explained, I don't actually think we are close to it. I think this theory of everything is just a theory of particle physics. So I want a theory of everything which is going to include, as you know, mind as well. But who knows how long that's going to be? I mean, maybe it will only be another 100 years. I mean, I don't think it'll be in my lifetime, but I do think it's conceivable that, you know, within another 100 years, we'll have a really final theory of everything, which is going to accommodate these things. And that's also remarkable because, after all, you know, we've been around, even Homo sapiens has been around, whatever it is, for 1 million years. So it seems incredible that in just a few years, a few hundred years, we're close to a final theory. Doubtless there is somewhere on another galaxy, there may be a civilization 1 million years more advanced than us. So how are they going to view us? Are they going to share the same final theory? I mean, it seems remarkable to me that after just a few hundred years, we may be close to a final theory. So maybe that's just very arrogant. Maybe we're nearly nowhere near a final theory. Maybe it will be another 1 million years. Or maybe we really are close to a final theory, and that will be even more remarkable.
Well, Bernard Carr, this has been a rewarding, fascinating, enlightening discussion, and as well as the three previous. Thank you so much for being with me. This has been a joy to me and a joy to be able to share it with our viewing audience.
My pleasure, Jeff, and I look forward to talking to you again sometime.
And for those of you watching, thank you for being with us.